Welcome to Chapter 3, where we explore the revolutionary transformer architecture and BERT. The 2017 paper, Attention is All You Need, fundamentally changed how we approach NLP. Instead of processing sequences step by step like RNNs, transformers use self-attention to process all positions simultaneously. BERT, released in 2018, showed how to leverage this architecture for unprecedented transfer learning. Together, these innovations set new state-of-the-art results on virtually every NLP benchmark. Let's understand how they work. The transformer architecture consists of an encoder stack and a decoder stack. The encoder processes the input sequence, while the decoder generates the output sequence. Each encoder layer has two main sublayers, multi-head self-attention and a feed-forward network. Decoder layers add a third sublayer for cross-attention to the encoder output. Crucially, each sublayer has a residual connection followed by layer normalization. This allows gradients to flow easily through the network. The original transformer used 6 layers each for encoder and decoder, but modern variants often use more. Self-attention is the core innovation of transformers. For each position in a sequence, self-attention computes how much it should attend to every other position. This is done through query, key, and value vectors. Each word's embedding is transformed into Q, K, and V through learned weight matrices. The attention score between two positions is the dot product of the query and key, scaled by the square root of the dimension. Softmax converts these scores to weights, which are used to compute a weighted sum of values. This parallel computation is much faster than RNN's sequential processing. Multi-head attention runs multiple self-attention operations in parallel. Instead of one attention function, we have 8 or more heads, each with different learned projections. Each head can learn to focus on different types of relationships. One head might capture syntactic dependencies, another might capture coreference, and yet another might focus on semantic similarity. The outputs of all heads are concatenated and projected to the original dimension. This gives the model more expressive power without significantly increasing computation, as each head operates in a lower dimensional space. Self-attention treats all positions equally, which means it has no inherent notion of word order. Positional encoding solves this by adding position information to the input embeddings. The original transformer used sinusoidal functions at different frequencies, creating unique patterns for each position. Even dimensions use sine, odd dimensions use cosine. This allows the model to learn relative positions, since the encoding for position k plus offset can be expressed as a linear function of position k's encoding. Modern models like BERT use learned positional embeddings, while newer architectures experiment with relative and rotary embeddings. BERT, which stands for bidirectional encoder representations from transformers, uses only the encoder part of the transformer. Its key innovation is truly bidirectional pre-training, where each word can attend to both left and right context simultaneously. BERT is pre-trained on 2 tasks: masked language modeling, where 15% of tokens are masked and the model predicts them, and next sentence prediction, where the model learns to identify if 2 sentences are consecutive. The input format uses special tokens: CLS for classification, SEP to separate sentences, and learned segment embeddings to distinguish sentences. Let's dive deeper into BERT's pre-training objectives. In masked language modeling, 15% of input tokens are selected for prediction. Of these, 80% are replaced with mask, 10% with a random token, and 10% are unchanged. This variety prevents the model from only learning to predict mask tokens. The model must predict the original token using bidirectional context. Next sentence prediction trains on pairs of sentences, with 50% being actual consecutive sentences and 50% being random pairs. The CLS token's output is used to classify whether the pair is consecutive. This helps with tasks requiring sentence-level understanding. Fine-tuning BERT is remarkably simple and effective. You take the pre-trained BERT, add a small task-specific layer on top, and train on your downstream task with a small learning rate. For classification, you use the CLS token's output with a classification head. For token-level tasks like NER, you use each token's output. For question answering, you predict start and end positions in the context. The key is that BERT's rich representations transfer well to diverse tasks. With just a few epochs of fine-tuning on small datasets, BERT achieved state-of-the-art results on 11 NLP tasks simultaneously. BERT inspired numerous variants and improvements. Roberta showed that removing NSP and training longer with more data improves results. Albert reduces parameters through cross-layer sharing and factorized embeddings. DistilBERT uses knowledge distillation to create a smaller, faster model that retains 97% of BERT's performance. XLNet uses permutation language modeling to capture bidirectional context differently. Electra replaces masked tokens with plausible alternatives and trains a discriminator to detect them. For multilingual NLP, models like MBERT and XLM Roberta extend these capabilities across 100+ languages. Let's summarize Chapter 3. We learned how transformers revolutionized NLP by replacing recurrence with self-attention, enabling parallel computation and better long-range dependency modeling. Multi-head attention provides multiple perspectives on relationships. Positional encoding preserves sequence order information. BERT demonstrated the power of bidirectional pre-training with masked language modeling. Fine-tuning allows us to adapt pre-trained models to diverse tasks with minimal data. The Hugging Face Transformers library makes these models accessible to everyone. In the next chapter, we'll explore large language models like GPT and how they've taken NLP to new heights.